Okay, let's see. So, oh, whoops, I'm in the wrong class. Hold on. Crap. Okay, great. Now we're here. All right, so I have your quizzes graded. I've uploaded them, so you should be getting them back. I just haven't put them in Canvas yet. Normally, because you're not, I think there's the registration is hung up a little bit delayed for a few of you. Most of you are in the class. I'll have them up on Canvas for you pretty soon. So what you'll notice when you log into Canvas, and I'm going to come back to this page in just a minute, but when you log into Canvas and access the course, like when you activate and can get in, over here on the left side, there's this like menu of items here, and if you click on assignments, every graded thing lives in the assignments link. So if you click in assignments, there'll be a link here. You'll see a spot for I'm in the wrong class again in Canvas. Okay, it's Monday morning. Let me get in our class. Okay, so you click on assignments, and then there's a link here for quiz 1, and if you click on it, this looks a little bit different because I'm the instructor, but you should see, once I put it in, you should see your score, and then you'll see a PDF of your graded quiz. So I should have that up later today for folks who are like officially on the roster, and then all of you will officially be on the roster. There's just a little delay for a few of you right now. So my plan for today was to spend time going over questions you might have. Does everybody have the problem set?
Yeah.
Great, perfect. So to go over questions you might have on the problem set or the practice test, which is that's posted to Canvas. So there's a practice test that's posted to Canvas. Actually, all the practice tests are posted to Canvas right now. So you could spend time on those. If you have questions on those, or questions on the problem set, or questions on the exercises, what I want to do is first spend time going over those questions. If you run out of questions, I'm ready to jump into the material in the next chapter and talk about limits. Who's got questions? Any questions? Yeah.
So the first one on the packet.
Is there a question just like how do we get started, or?
Yeah, sort of.
Okay, let me just bring it up here. So the first thing I want to just draw your attention to is this note. You know, read the instructions here. There's a note here to let you know that, you know, guess and check can be a great way to get started on a problem, but it is not a technique that if you rely solely on, you're going to get full credit for. We want to arrive at our solutions. We want to present full solutions on like, here's how I know, here's how I arrive at it. And not just find answers, right? So like the focus on in this class, aside from just like the specific calculus material, is on writing nice, like coherent, convincing solutions. So we want to make sure that we're using an algebraic approach to these problems. And I mention that specifically right now because a lot of the time people can kind of stumble on the correct answer to this one without actually putting in a full solution. So this problem says we want to find the equation of the line. All right, so we're looking for the equation of some line. And we know a point that it passes through. It passes through the point 3,2. Perfect. So what else do I need to get the equation of this line? Another point, or if I just knew the slope for some reason, you know, like another point or the slope explicitly. If I knew another point, I could find the slope. So we want the equation of this line. It passes through the point, and then it says, and forms with the axes a triangle of area 12. Then find the area of the triangle. Or the angles of the triangle. So I'll tell you one quick note, like you might want to like highlight or underline or just draw your attention to this a lot of the time because it takes a bit of work. Notice under the box here it says times 2. This is a times 2 problem. So it's going to take a bit of doing to write out the solution. After people find the equation of the line, and there's a lot of work that goes into that, sometimes people just forget to find the angles of the triangle. Like I know we all are going to be able to do that, but sometimes it just, you do so much work and then you're like, oh, I'm done, and then you move on to the next question. So just make sure that you find those angles after you get that equation. Okay. I'm just going to start this out. We know that it passes through the point 3, 2, and then there's an area of the triangle is 12. So I'm gonna, I think it'll help to visualize this a bit. If it passes through the point 3, 2. And then it says the line goes to this point and it forms with the axes a triangle of area 12. So I think we're looking at something like this. And so the triangle they're talking about is this triangle right here. So there's a couple of pieces of information they've given us. And I just want to see if we can't, write down some equations. Obviously, the big barrier here is that I only have one point. So we could label these other points, give them names. Like, if I look at this point on the x-axis, right? I don't know the x-coordinate, but I definitely know the y-coordinate, right? What's that y-coordinate? 0, yeah. And same over here, right? The point on the y-axis, I don't know the y-coordinate, but I know that the x-coordinate has to be 0. So I'll just give those coordinates names, right? Like, I don't know, maybe I'll use A for the x-coordinate over here and B for the y-coordinate up there. We don't know what they are, but okay, fine. Let's focus for a minute on the fact that the area of this triangle is 12. It's a right triangle. Like, what do we use to find the area of this triangle? Like, if I knew like all the measurements, like how would we get the area of a triangle? 1/2 times base times height. Yeah, good. So look at how we've labeled those points. Do we have a name for the base over here? Like what would, given how we've labeled these points, like what should this length be? A, yeah. And what about this vertical length? Yeah. Okay. So that's our base and height, right? The base and the height, like what makes them a base and a height is that they're perpendicular to each other. So with the right triangle, you just use the two legs for your base and your height. So this gives us 1/2 base height, 1/2 AB. And we know that this area is 12. They told us. So that gives us an equation, 12 is equal to 1/2 AB. So I'm going to pause there for a moment and just say, look, if I knew what either the value of A or B was, we would be all set to find the equation of our line, because we would have actually 2 points, right? We'd have both. We'd have 2 fixed points. We would be able to find the slope, and then we'd be good to go. So here we have this equation with A and B. One equation with A and B. I've got 2 unknowns. How many equations do I want to have?
Say it louder. 2.
2. Yeah, if you have 2 unknowns, we want 2 equations. So we have 1 equation. That's progress. All right? We could even rearrange it if we multiply both sides by 2 and say, well, 24 is AB. Now, I'll tell you right now, before we talk about how to get the other equation, one mistake that people make is they say, oh, well, there's only a finite number. I'm just going to check things that multiply out to 24. So I got 1 and 24, 2 and 12, 3 and 8, and 4 and 6. And these axes, those are real number lines. There's actually infinitely many values you can multiply to get 24. For example, 48 and 1/2, or the square root of 24 and the square root of 24. There's infinitely many combinations. There's nothing that says that these have to be whole number values. So that's an assumption that we don't want to make. If we think about how we could get the other equation that we need, let's focus now on the line itself. All right, we know it goes to the point 32. We don't know what its slope is, but look, what if I found an expression for the slope? What if I found an expression for the slope using this point and this point, the 2 intercepts? What would that be? Or how do we find it?
Would it be A minus, no, it would be 0 minus B over A minus 0?
Right, so like rise over run, right? Difference in y's over difference in x's. Nice. What does that simplify to?
Negative C over X.
Great. So there's an expression for the slope. Now I'm going to just say, what if, you just need 2 points, right? You pick 2 points and make a slope. So there I used the 2 intercepts. What if, I don't know, what if I use the y-intercept and the 0.32 this time? What would that look like then?
B over 3.
2 minus b over 3, right? Because it's 3 minus 0. Great. So look, we have these 2 different expressions for the slope. What can you tell me about these 2 expressions? They have to be. They're both the slope of the same line, right? The line is a fix. It's got one slope, whatever it is. There's your other equation. Those 2 things have to be equal. So then you end up with 2 equations and 2 unknowns, and you could dive into the algebra to solve. I think when I worked it out, eventually it boiled down to I ended up having to solve a quadratic. So don't be afraid of the algebra, but that'll kind of get you started. Once you have figured out what A and B are, you can find the equation of the line, like the way we know that we can, right? All you need are 2 points, and you get the equation of the line. And then don't forget to find these 2 angles. So these are the angles that you want to find here. Other questions? Other problems on the problem set you want to ask about? I mean, there'll be more time to ask questions in class on Wednesday and Thursday, too. So if you don't have any right now, that's okay. But just, make sure that you do, put in some time. I think I'm probably already said this. I like to repeat myself, though. You want to give yourself time to get stuck, right, on a problem and ask for help. Okay. If there aren't any other questions right now, then we'll jump into talking about limits, I guess. So in this new chapter, now that we're in chapter 2, and for the remainder of the semester, these exercises, with some exceptions, I'll announce it if I've got some practice in a handout or something. But for now, pretty much all of the exercises are coming from that Larson text. So we're starting in chapter 1, talking about limits. So what we're doing right now is kind of building the tools and the concepts we need to ultimately define what we're calling the derivative of a function. That's the chapter of this title. Don't worry about what that means just yet. But foundational to all of calculus, what is like a huge foundation in calculus is the concept of a limit. So we need limits. We need limits for functions that have weird behaviors at certain points, right? If everything was smooth, and if everything, didn't have any hiccups, or there was nothing weird that happened in the function, we probably wouldn't need limits. I don't know if calculus would have been, developed or discovered if without the need for this concept. But the whole idea of a limit is saying, suppose I have this function, and here I've just graphed an arbitrary function in this definition. And it says, look, as x gets closer and closer to some value, say I'm calling it c here, if I kind of trace the function, right, as x gets closer to that value, and then I see what are the y coordinates zeroing in on as I get closer and closer. That's what the limit is. We say that the limit of f of x as x approaches c, and that's how we say this right here. This is the limit of f of x as x approaches c. Is equal to some value L if the function values just get closer and closer to L as x gets closer and closer to c. That's like our intuitive sense of what a limit is. It's really important to note that our function doesn't even have to be defined at c. And in fact, really, I think the whole idea of a limit was necessitated because people were dealing with functions and we had some value, maybe isn't in the domain, maybe I can't plug it in, but I still want to know what happens as we get close to it. And that's what a limit is. I'm going to just throw this other definition out there. I think you'll probably see it in Larson also, but we call this the Epsilon-Delta definition. And And here's how it goes. It says that the limit as x approaches c of f of x is equal to L if for every epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever absolute value x minus c less than delta. So here's what that means. First of all, in the real numbers, if you take the absolute value of a minus b, you know, you subtract two things and the absolute value, that is always the distance. You know, on the real number line, if we're just working with one dimension, the distance between two values is just the absolute value of a minus b. Now, what this epsilon-delta definition says, first of all, look at this, for every epsilon greater than 0. The idea here is like you could pick any value for epsilon that's greater than 0, and the idea is that you would pick something really, really small. Like I want to get, like that's saying how close do you want to get to the limit? If something is a limit, then you should be able to get to within any positive distance of that you want. It's easy to get far away from it, right? So the whole concept, the whole idea is like you might pick an epsilon that's super, super small, like get me really close. So imagine I've really zoomed in here, and so like this is a really crazy small epsilon. And what we do is sort of form what we call an epsilon band. Like there's the window. I want you to get me this close to the limit. And this definition says that L is the limit. If no matter what epsilon we pick, I can always find you a delta and say you'll be within epsilon of the limit as long as you get this close to C. And that's the epsilon-delta definition. But basically the whole idea is stated up there in the box on top. It's a limit if you just get closer and closer to that value as x gets closer and closer to c. So on the next page, we're going to do just a quick example that's more visual, graphical. So here's just, you know, there's no equation defining this function. I've just sketched out this is what a function might look like. Let's look at, you know, this nice smooth curve, except something weird is happening at x equals 3. Can somebody tell me what it means when we see this circle here? Say that again. It's a hole, right? So that means that f of 3 is not at that circle. It's not at that hole. But then now there's a solid dot up here. What does that mean? So there's a hole at on the curve there. We put a little hole. That means that f of 3 is not there. There's a solid dot above it, and that means that they've just sort of filled in the hole somewhere else. So like in this curve, in this function, the function values just lie all on this nice smooth curve except at 3. Now sometimes there's a hole and they don't fill it in at all, and that just means f of 3, you can't plug it in. It won't give you a value. Sometimes they fill it in and they put it somewhere else. So in this function, f of 3 is equal to 2, right? That's where the solid dot is. But the limit as x approaches 3, if I kind of trace along the curve, as x gets closer and closer to 3, the y coordinates get closer and closer to 1. So the limit doesn't have to be equal to the function value. The function doesn't even have to be defined in order for the limit to exist. What has to happen for the limit to exist is that it just has to be the same on either side. Like no matter what direction you approach 3 from, notice it didn't matter if I approached it from above or from below, the y-coordinate still got closer and closer to 1. That means that's what is required for that limit to exist. So we say the limit as x approaches 3 of f of x is 1, even though f of 3 itself is equal to 2. This is an example of a function that has a discontinuity. So we would say that this function is discontinuous or not continuous at x equals 3. The intuitive sense of what it means for a function to be continuous is that, like, I could trace it without having to lift my pencil up off the paper. What it means to be continuous, sort of in a more rigorous definition, is that these 3 conditions are met down here. I'm going to scroll down. I'm going to scroll back up again to kind of see what this means in the context of that example. But a function's continuous if it's sort of smooth, you know, or we talk about continuous at a point, if it sort of passes smoothly through that point, there with no jumps or holes or anything. In order for that to happen, first of all, the function has to exist. I have to be able to plug in the value and get a value out. The limit has to exist, which means I have to be able to approach it from either direction and get the same value. So if I'm approaching it from above or below, the y-coordinates are approaching the same value. And then here's the third thing is the function has to exist, the limit has to exist, and they have to be the same. Okay, so there's different ways or different reasons a function might not be continuous at a point. In this example, this function is not continuous at 3 because it fails that third criteria. The limit exists, the limit is equal to 1, the function exists, the function f of 3 is equal to 2, but they're not equal to each other. So the reason that this is not continuous is because it fails that third criteria in the definition below. This is an example of what we might call, and this, you don't necessarily need to write this down or anything, but sort of bonus material. This is what we would call a removable discontinuity, because I could make the function continuous there if I just redefined f of 3 instead of saying f of 3 is 2. If I just said, oh, let's make f of 3 equal to 1, then it's fixed, right? I've plugged in the hole, I patched it up. And I was, you know, you can make it continuous by making that one change. So we talk about, so this is what it means to be continuous at a point, C. And we say that a function is continuous on an interval if it's continuous at every point in that interval. So here, in this function up here, it looks like this function is continuous everywhere else. So it's only, you know, at x equals 3 is the only discontinuity. It's continuous. It's continuous here. It's continuous here. It's continuous here. Everywhere else it's continuous. So on the next page we're going to sort of play with this idea of continuity. We're going to identify spots where it might be continuous or not continuous. Or usually when we think about continuity or finding where it's continuous, we kind of come at it from the back door and we say, well, where is it not continuous? Can we find any problems with continuity? So we got the first 3 are just by looking at the graph. Are there any discontinuities here? No, it looks pretty smooth. We would say, I think there's a domain restriction, right? It looks like the domain of this function in part A seems to start at 1, right? Because there's no graph that exists before x equals 1. So we would say that this is continuous on its domain. How about the graph in part B? Any discontinuities there? Say that again?
Yeah.
Where?
It like breaks at 1.
Yeah, it looks like it's at 1. So we could sort of identify pretty quickly there's some funny business going on where we see that hole, and also like there's kind of a gap right between where one side of the function ends and the other side of the function begins. So this is not continuous, or is discontinuous at x equals 1. And which of the criteria does it fail? Like if we look at that definition on the last page, does f of 1 exist? Could we plug in 1 and get out a value? It looks like it's maybe around 5 or something, right? Like f of 1 exists because of that solid dot right there, so that seems to be okay. Does the limit exist? What do you think? Does the limit exist for this? Or maybe to help you answer that, try to figure out what the limit is. Can you tell me what the limit is? What's that? Did I hear a no?
Would it be null since there's sort of 2 limits?
Yeah. And there's the thing, there can't be 2 limits, right? In order for the limit to exist, you have to be approaching the same y coordinate no matter what direction, whether you come at it from below or above on the x-axis. This seems, if I approach it from the left, it looks like it's getting close to 3. And if I approach it from the right, it looks like it's getting close to like 4.5 or something. So those are not the same. The limit doesn't exist, and that means it's not continuous. How about looking at the graph in part C? Where is it not continuous?
X equals -2.
Yeah. And can we figure out why, like, which of those three criteria on the last page does it fail?
First one.
Yeah, the function doesn't exist. There's a hole, right? F of -2 does not exist. Looks like it's continuous everywhere else, and that's true of the last one too. You know, like we found the problem. We found a point where there's a problem, a value of x where there's a problem, and everywhere else it's pretty smooth. So these first three we did, you know, we kind of assessed its continuity by just looking at its behavior on a graph. And now we're going to do a couple examples where we assess its continuity, where we're just given the equation. So, you know, algebraically, if I'm looking for any issues with continuity, the things I'm looking for are primarily like looking out for division by 0 is a big one. So in this case, in part, you know, this f of x is 1 over x minus 2. There's a value of x I'm not allowed to plug in because it'll make me divide by 0. And f of 2 does not exist. 2 is not in the domain. So there's a discontinuity there. I can't plug in 2. You could see like some, I'm gonna just sort of pull up the graph real quick. We, in the previous three, you know, when we were looking at the graphs, we mostly we saw some jumps or holes or gaps, right? And we're kind of able to see that as a discontinuity. In this kind of discontinuity, if we look at this graph, so we have a vertical asymptote, and that often happens in places where we divide by 0. Not always, but often that'll be the behavior of a graph near a place where we're going to have to divide by 0. We get this vertical asymptote. So as x approaches 2 from either direction, it either kind of shoots upward towards infinity or down towards negative infinity. And we say that this is an infinite discontinuity. The other way that you might see discontinuities, if you're just looking at a function like written out like this, they just give you the formula. The other thing to look out for are piecewise defined functions. So if we go up here to this, the one in part B, if we were given an equation or the expression for the function, it would be given in some form like this. There'll be like a curly brace, and then they would say it's some expression, you know, blah, 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 for x less than 1, and then some other one for x greater than or equal to 1. That's what it would look like. Because they're clearly like totally different behaviors on either side of that point. So if you're looking for discontinuities, you want to be on the lookout for division by 0 or these piecewise defined functions. It's not that a piecewise defined function always has a discontinuity, but it certainly can lead to discontinuities, and you just want to pay attention to what goes on right at that spot where there's a, you know, they break up the domain. What about in part E, 3x squared? Is there any risk of division by 0? No, it's not. It's certainly not a piecewise defined function. We can square anything, right? There's no problems with squaring a number. Sometimes you got to be careful if we're taking square roots. That'll restrict the domain. But you could square anything. So this is actually continuous on all real numbers. No discontinuities at all. And if you know a function's continuous, the cool thing about knowing a function's continuous is that if I want to find a limit at some value, I just plug in the value, right? Because if the function's continuous, then the limit is equal to the function value, right? They both exist and they're equal to each other. So we have this sort of concept of a limit. We have like an intuitive sense of what a limit is and you know, what it looks like on a graph, how it's related to this idea of continuity. And we're going to get some practice evaluating limits. There's a couple different techniques. We're going to do an example where we evaluate a limit numerically. And then we'll kind of put most of our focus on evaluating limits analytically. So numerically, if I want to know a limit, if I'm trying to figure out what a limit is, you know, the concept, I could use that whole idea of what a limit is and say, well, as I get really close to this value, what are the y coordinates getting close to? Just like make a little table, like keep plugging in values that are getting closer and closer to that number. So we want the limit as x approaches 3 of x squared minus 9 divided by x minus 3. So if we're doing this numerically, I'm going to just make a little table. I'm going to compare, I'm going to plug in values of x that get closer and closer to 3. I have to let x approach 3 from below and from above. So I'll plug in like 2.9, 2.99, 2.999. And then I'll plug in 3.1, 3.01, 3.001. Now, when you're doing this and keep plugging in functions, or plugging in values to the same function over and over again, that can get a little tedious. What I like to do is actually plug in, like enter this expression into my y equals editor. So x squared minus 9, I have to make sure I put both the numerator and denominator in parentheses. There it is in my calculator. Once I've got it entered in, I'm going to quit back to the home screen, so second mode to quit. And I'll just note before I plug stuff in, we can't plug in x equals 3. Right? Like if I plug x equals 3, it's going to make me divide by 0. So that's sort of why we have to go through this rigmarole, kind of set up this table and get closer and closer to that value. But now so I've got the function entered, I'm at the home screen. Next to the clear button is a button that says vars for variables, so I'm going to hit that. And y vars. At the top, I'm going to arrow over to the y vars menu. And then the very first option is function. I put that into my function editor, so I'm going to hit enter. And now it's bringing up all these functions. I put mine in y1, so I'm going to hit enter to access that function. And then it's just regular function notation. So I want to plug in 2.9. So I'm going to do parentheses, 2.9, close parentheses. So that's like f of 2.9 is what I'm finding. And it'll tell me what it is, 5.9. Again, if I want to plug in 2.99, vars, y vars, function, y1, 2.99. And I get 5.99. The nice thing about doing this on the calculator like this is I could, once I've entered it and I've gone through to select the y1 function, I can just pull up my previous entry. If you hit the second button and enter, see it says entry in blue above that key. So second enter will bring up the thing I just entered. So I'm going to use my arrow keys and now do 2.999. negative 5.999. It looks like it's getting closer and closer to 6, but we have to make sure it also is approaching the same value from the other direction. So 3.1, I get 6.1, 3.01, 6.01, 3.001, oops, 6.001. So it kind of looks, it kind of appears like these values are getting closer and closer to 6. Now, the best we could do, if we're evaluating a limit numerically, really the best we could do is say it looks like the limit as x approaches 3 of x squared minus 9 over x minus 3 is equal to 6. I mean, weird things can happen with functions. Maybe it's possible you could get really odd behavior, but you have to get so close to 3 before you start seeing that happen. So we could say it kind of looks like that this limit is 6. It isn't very definitive. It's semi-convincing. I would call it semi-convincing. Might get you to the I believe it stage. What we want to do is be really convincing. We want to create a convincing argument and show for sure this limit is equal to 6. We're going to do a couple of examples. We're going to do one example, and then we'll return to that limit in particular. So if your function is continuous, as I mentioned before, if your function is continuous at a value and you want to find a limit as x approaches that value, just plug it in. So x squared plus 2 as a function, that's continuous. You can square anything. It's not piecewise defined where there's no risk of division by 0. That's continuous everywhere. And in particular, it's continuous at negative 2, which is the value that we're interested in. So if I want to evaluate this limit, I'm just going to plug in negative 2. So we get 4 plus 2, or 6. This limit is for sure 6. It's continuous. I just get to plug it in. The problem in the next, the problem with the limit that we just looked at before, that we did numerically, and that we're going to look at again, the problem with this limit is that I want to evaluate this limit at a value where it's not continuous. If I wanted to evaluate this function, the limit of this function as x approaches 2 or 5 or negative 7, I could just plug that in. That would be no problem, because this function here, the x squared minus 9 over x minus 3, that's continuous at those points. The only place where it's not continuous is at 3, and that happens to be what we're interested in. So what we're going to do is a little bit of algebra. So I'm going to rewrite this. This is equal to the limit as x approaches 3. Now the top is a difference of squares, so we can factor that. That's x minus 3, x plus 3. All over x minus 3. What are we going to do now? Yeah, we're going to cancel out the x minus 3. So now this is equal to the limit as x approaches 3 of x plus 3. And you know what's cool about x plus 3? What's cool about x plus 3? What's that? I still didn't hear you. I'm sorry.
They're saying it's continuous.
Oh, great. Perfect. See, I heard that. Say it with feeling. The microphone's way at the front of the class. It's continuous. It's continuous everywhere, but we only need to be continuous at x equals 3. And it is. So we can plug that in. And this limit is in fact equal to 6. We had our suspicions above. Now we've shown it for sure. Now here's an important piece of this, of working out this problem. We used algebra to rewrite this. And as we went through, we kept the limit. The limit as x approaches 3, the limit as x approaches 3. That's really important. Because x squared minus 9 over x minus 3 isn't always equal to x plus 3. They're equal almost everywhere, but they're not equal at the very value that we're interested in, right? If you compare x squared minus 9 over x minus 3 to just x plus 3, the really important difference is that this x plus 3 is defined at x equals 3. We can plug it in. This is not defined. They don't have the same domain, but they do have the same limit. And that's why we can carry this continuity, or this equals, as we go through. It's because we've kept the limit. They're not equal completely as functions, but their limits as x approaches 3 are equal. And so it is imperative that we keep the limit as we go through this process. And we're allowed to drop the limit at the moment that we let x approach 3. So that's why on this line, I didn't write lim anymore. I actually plugged in x equals 3, because that limit is equal to 3 plus 3, which is 6. So we want to just make sure that we're communicating what we mean, right? For, when we're in algebra and pre-calculus, we don't worry about the limits because we're mostly like looking at kind of a macro behavior, like, yeah, these are the same. They're the same almost everywhere. In calculus, we're really starting to focus on where are they not the same, and then using algebra to kind of help us with these limits. Let's do another one. And before we do that, actually, are there questions on this example? Okay. So now we want to evaluate the limit as x approaches 0 of the square of 4 plus x minus 16. The first thing I'm going to do when I see a limit, the first thing I do is just see, well, can I plug in the value? Can I plug in this case, x equals 0? And pretty quickly we find that we can't, because it's all divided by x, and clearly that would make us divide by 0. So that's a problem. So we're going to do the same thing. These limits as x is approaching a specific value that makes us divide by 0, our approach is, can I use algebra to rewrite it and cancel out that problem factor? So if, like up here, the previous one, if I couldn't, if the top didn't have a factor of x minus 3 that I could cancel out, then the limit wouldn't exist, right? Or it would be like infinite. We'd have a vertical asymptote if you graphed it. But as it turns out, this, it did have a factor. If you graph x squared minus 9 over x minus 3 and x plus 3, in the calculator, it'll look identical. And it is identical everywhere except at x equals 3. Like this fraction is a line with a hole in it. And then the x plus 3 just has the hole filled in. So here we're going to use algebra to rewrite it. Hopefully, if, maybe there's a factor of x up top. It's kind of hard to determine just right now, but we could do some factoring. There's two ways you could approach this factoring problem, and they'll both get you the same place. So if you were looking at this problem, like, what do you, what's a way we could start if we're looking to rewrite the top?
Well,
Sure. Yeah, let's FOIL that out. So if you FOIL that out, we get 16 plus 8x plus x squared minus 16. These, the 16 and the minus 16, those cancel. So we're left with just 8x plus x squared. What can we do with that?
We factor out an x.
Yeah, let's factor out an x. Now those x's cancel. I'm carrying through the lim in all of these calculations, so this is equal to the limit as x approaches 0 of 8 plus x. What is that limit equal to? Yeah. So there we are. The other option, just because of how this was written, is you could see this as a difference of squares and factor it as 4 plus x minus 4, 4 plus x plus 4, and that will still get you to the same x times 8 plus x. Questions? Okay. All right. So this is one type of limit that we'll be calculating, these limits as x approaches some constant. Here it was as x approaches 0, in the last example it was as x approaches 3. But we will also find it helpful to be able to evaluate limits as x approaches infinity. And we should be really careful here and hyper aware of the fact that infinity is not a number. You can't do arithmetic on it. Infinity divided by infinity is not always 1. Sometimes it's 2, sometimes it's -3. You know, we don't know. It's not a number. What we're doing when we evaluate a limit as x approaches infinity, if we want to kind of visualize this, if we're looking at a graph of a function, we're trying to figure out what is the behavior as x gets large. Like, does the function kind of level off? Like, does it have a horizontal asymptote? Does the function blow up? Like, that's the kind of thing that we're after. When we evaluate these limits analytically, what we use, our strategy is that we know what happens. Like, so we have this example in 2.7. I'm going to just do a quick mini example on the side here. Suppose I just want the limit as x approaches infinity of 1 divided by x. As x gets huge, what happens to 1 over x?
Smaller.
Yeah, and is there any value that it keeps getting closer and closer to?
0.
0, right? We can make it as small as we want if we let x get big enough. So this limit is 0. And in fact, more generally, the limit as x approaches infinity of any constant k over x to the n, as long as n's a positive exponent and k is any constant at all, even if k is like a million, right? Like, even if k is a big constant, that limit is going to be 0. So what we want to do when we're looking at limits is we're hoping that we'll see any instance of x appear as being in the denominator of some fraction with a constant numerator. Like, we want everything to appear like that because we know those go to 0. So that's what's happening in 2.7, right? The only time that x appears is in the denominator of that fraction. So I know that that fraction goes to 0. And of course, 1's a constant. 1 just stays put. So somebody tell me, what is the limit as x approaches infinity of 1 plus 1 over x?
1.
It's 1, yeah. So this is our strategy. We're going to start with limits where, you know, we have a limit as x approaches infinity, we got some expression with x's. We're going to do algebra to get it so that every time x appears, it's as the denominator of a fraction with a constant numerator. It's going to be in the form of something that we know goes to 0. And the way that we accomplish that is we're going to divide the top and the bottom by the highest power of x that appears, or multiply by 1 over the highest power of x that appears. So let's see how this works in the next example. I've got x squared plus 1 over 2x squared plus 3, and I want to see what is the limit as x approaches infinity. As x gets huge, like if I start plugging in huge numbers, 10,000, 100,000, 1,000,000, 2,000,000, whatever, what value, does this function approach a single value, or does it blow up, or whatever? So the highest power of x that appears here is x squared. And we're going to start by multiplying the top and the bottom by 1 over x squared. And we're going to distribute that factor of 1 over x squared. If we distribute up top, what do we get? Yeah. And then let's do the same thing on the bottom. What do we get there?
Now,
Plus 3 over x squared, yeah. Good. Now we've accomplished that intermediate goal. The only time x appears here is in the denominator of a fraction with a constant numerator. So as x gets huge, what happens to 1 over x squared?
it's smaller.
Yeah, in fact, it approaches 0. I mean, I wanna say like get smaller and smaller. Like something that approaches 1 from above also gets smaller and smaller and smaller, but there's like that limiting, value of 1. We want to say not only does it get smaller and smaller, it really diminishes to 0. It never gets to 0. There's no number I'm going to plug in where it actually gets to 0, but I can get you as close to 0 as you want me to get. And then 3 over x squared. Again, that approaches 0. So somebody tell me what this limit is.
1/2.
Yeah. 1/2. Let's try one more. This one's kind of fun. It's a similar type of limit as x grows without bound. And this time our function is the square root of 3x squared plus 5, all divided by 2x minus 1. At first it kind of looks like the highest power of x that we have is x squared, but that x squared is hiding inside a square root. So in effect, the highest power of x that we really have is just x to the first. What we're going to do is multiply both the top and the bottom by 1 over x. Now, before we do that, I just want to point out, sometimes people see this fraction and they want to square the top and the bottom to get rid of the radical. We're not actually allowed to do that. We can't just square the top and the bottom of a fraction because that's squaring the whole thing and now the expression isn't the same. Like we can't square 1/2, the top and the bottom of the fraction 1/2 without changing its value to 1/4, for example. So that radical stays, but we can use other properties. Let's deal with the bottom first. That's a little bit simpler. If I distribute 1 over x, what do we get?
2 minus 1 over x.
Great. Okay, now up top. I'm gonna just really quickly, we did this the other day. We simplified a radical. I think we had something like the square root of 12, and we said, oh, that's 2 times 2 times 3, or 2 squared times 3. And what we're used to do is saying, oh, I've got a perfect square and a radical, so I can pull that out as a single factor of 2. And so we got 2 root 3. But this property of like perfect squares inside becoming a single factor outside also works in reverse. If I have a single factor outside a radical, I could throw it in the radical. I could say, oh, let's throw that in, and I'm allowed to as long as I square it, so that 2 would become a 2 squared inside. That's what we're going to do to this factor of 1 over x through that radical. We're going to throw it in there, and we're allowed to do that if we square it. And the square of 1 over x is 1 over x squared. So now I've got a factor of 1 over x squared in the radical, and that's helpful because that's something we can distribute. Now I can distribute that through the parentheses in the radical. What do we get?
Three over x plus 5 over x squared.
Say that again.
3 over x plus 5 over x squared.
Not 3 over x. The 5 over x squared is correct. But we have 3x squared times 1 over x squared.
Oh, 3.
Yeah, just 3. Great. So now we've accomplished that intermediate goal. Every place x appears now is in the denominator of a fraction with a constant numerator. So somebody tell me, what does 5 over x squared approach as x gets huge? Yeah, and what about 1 over x? Approaches 0. So we do all this algebra to make the limit then like simple, right? And what is this limit equal to? Square root of 3 over 2. And I'll just say this is a nice example to do to see why we don't rely on something just evaluating limits numerically. Like, you know, if we just set up a table, we would get close to the approximation of whatever root 3 over 2 is. But you know, we're never going to arrive at root 3 over 2 or be able to kind of tell that that's the pattern that's leading to. So again, I'm carrying the lim through at each step until I let x blow up, until I let x grow without bound and see what things are getting close to. And it is at that moment I no longer need the lim there because I let x approach infinity. Questions on that example? Okay. All right. That's all I want to get through today, and we're pretty close to being out of time. So there's some practice exercises. I'm sure your priority is probably working on the problem set and getting ready for the test. So when we have class on Wednesday, again, I'm going to start class by seeing what questions you have. And in the absence of questions, you know, we could keep working through that chapter, but spend some time on the practice exercises or the problem set and the practice test. You know, we'll answer questions for as long as you have them on Wednesday before we talk about slope of a tangent line. Enjoy the rest of your day, and I'll see you all on Wednesday.